Hi, I'm Karthik, and this is Lab 4, Circuits. So today, we're going to introduce this lab with the purpose and the fundamental principles used. Then we'll go over the procedure and show the data and results we obtained. Finally, we'll go over the reasonability of these results and answer any final questions. The purpose of this lab is to predict the behavior of circuits with resistors in parallel and in series. We will also see how charging and discharging a capacitor works and use the loop rule and conservation of energy to see how close actual values of conventional current and potential voltage difference are to theoretical values. The main principles we use in this lab are charge and energy conservation, and for RC circuits, time-dependent voltage across a discharging capacitor. To start, we need to install the circuit construction kit from Colorado FET. The procedure is listed in the lab manual and explains the steps to construct and examine time-dependent voltage across DC and RC circuits. We'll go into more detail later with each circuit. The first circuit is DC and has two 1.5 volt batteries and two resistors of 100 ohms and 47 ohms respectively, all in series. The calculated current is 0.0204 amps as found through Ohm's law, and when adding the two ammeters to the circuit, we can see that the current is 0.02 amps. When flipping the ammeter the other way, you still get a current of 0.02 amps. This is because it shows the magnitude of the current, or the absolute value. In continuing the procedure, we were instructed to replace one of the ammeters with a voltmeter. The voltmeter showed a 3 volt drop from one side to the other, and the ammeter read 0 amps as the circuit is open and there's no current flowing through the voltmeter. This is because there is a theoretical infinite resistance within the voltmeter, which allows for no current to pass through. Closing the circuit without the second ammeter, I used the voltmeter to calculate potential difference at 8 pairs of locations across the circuit. When adding up all the voltage differences, we get a net of 0 volts, which confirms the loop rule. Here's a simple graph of the potential drops throughout the circuit. From A to B, the voltage climbs to 1.5, then up to 3 volts, and stays at a constant till C to D, where the first resistor causes a voltage drop of a little less than 1 volt, then stays consistent till the second resistor causes a voltage drop of a little more than 2 volts down to 0. The first question asks why adding the voltmeter doesn't change the reading on the ammeter. This is due to current only being dependent on voltage and resistance through Ohm's law, and neither of these values change due to the voltmeter. This is confirmed by showing that connecting the voltmeter across the 100 ohm resistor keeps the ammeter at 0.02 amps. Finally, if we add an ammeter in parallel with the 100 ohm resistor, the current goes up to 0.06 amps, and this is due to the current taking the path of least resistance across the ammeter instead of the resistor. Using Ohm's law, we can calculate the real resistance of each resistor. Simply put, we get this by dividing the voltage difference across the circuit item by the current. For the 47 ohm resistor, we get almost 48 ohms, and for the 100 ohm resistor, we get a value of 150 ohms. And for the wire and the ammeter, we get 0 ohms as there is no voltage drop for either of these. Now on to the RC circuit, with a 10 ohm bulb, 9 volt battery, and 200 microfarad capacitor. The light bulb starts off bright and slowly becomes dimmer until there's no current in the circuit and no light. This is the same circuit without the battery but with a charged capacitor. The capacitor has a stored charge, and essentially the same thing happens to the circuit and the light bulb, but the current flows in the other direction before coming to a stop. The current in this RC circuit decreases as the capacitor is charging. Right after we removed the battery from the circuit, the current jumped up to around its original level and discharged slowly. When I manually timed it, the capacitor charged in 9.8 seconds and discharged in 10.42 seconds. I performed the same experiment with the 20 ohm bulb and it took around twice as long. Theoretically, these two values should be the same, but I manually timed them and thus they're a little off. This is a graph of the RC circuit ln of V over VO versus time. The RC constant is resistance times capacitance. The slope of the ln V over VO graph is negative 1 over RC. The slope of our graph was negative 0.1665, which means that the RC was 6.006 seconds. The theoretical value for RC of this circuit is 6 seconds. For a reasonability check, it makes sense that these values are close, because this is a simulation and the code that makes it work is based on these values. If I did this lab in real life, the ammeter readings would be lower because there's resistance we don't account for in the wires. In our ideal model, the capacitor seems to instantly reach full charge in a circuit with no resistor. The This wouldn't happen in real life as the wires themselves have some resistance. I think it would be interesting to see how different these values would be if we use a real circuit in these less than ideal situations. Thanks for listening to my lab.